MPLS multi-protocol label switching, MPLS, is a high-performance telecommunications technology that directs data from one network node to the next based on short path labels rather than long network addresses. It was designed to combine the speed of Layer 2 switching, like ATM, with the routing capabilities of Layer 3, IP. Key concepts of MPLS. To understand MPLS, you have to look at how it changes the decision-making process of a router. Label-based forwarding. In traditional IP routing, every router performs a complex longest match lookup in a routing table for every packet. In MPLS, the first router, ingress, does the lookup and attaches a label. All subsequent routers simply look at the label, swap it, and pass it on. This is much faster and allows for traffic engineering. Key terminology: LER, label edge router, the entrance and exit of the MPLS network. It adds, pushes, or removes, pops, labels. LSR, label switching router, the core routers that only look at labels, swap them, and forward the packets. LSP, label switched path, the predefined, unidirectional path that a packet takes through the MPLS network. FEC, forwarding equivalence class, a group of packets that are treated the same way, example, all packets going to a specific IP range get the same label. The MPLS header, the shim header, MPLS is often called a Layer 2.5 protocol. This is because the MPLS header is shimmed between the Layer 2 header, like Ethernet, and the Layer 3 header, IP. The MPLS header is 32 bits, 4 bytes, long and contains 4 specific fields. One label, 20 bits, this is the most important part. It holds the actual value used by the routers to make forwarding decisions. With 20 bits, there are over 1 million possible label values. 2TC, traffic class, /EXP, experimental, 3 bits, originally called experimental, these bits are now primarily used for quality of service, QoS. They allow the network to prioritize certain packets, like voice over IP, over others, like background file downloads. 3S, bottom of stack, 1 bit, MPLS allows for label stacking, multiple labels on one packet. Value 0, there are more labels following this one. Value 1, this is the last label in the stack, the bottom. Application, this is crucial for VPNs, where one label routes the packet through the core network, and a second label identifies the specific customer's private network. 4 TTL, time to live, 8 bits, just like in IP, this field prevents packets from looping forever. Every time a packet passes through a router, the TTL is decreased by 1. If it reaches 0, the packet is discarded. The MPLS header structure table field length description label 20 bits, the identifier used for switching and path selection. TC, EXP, 3 bits used for quality of service, QoS, and ECN. S, stack, 1 bit indicates if this is the last label in the packet. TTL 8 bits prevents infinite loop, time to live. How MPLS works: MPLS simplified the core of the internet by replacing complex IP lookups with simple label swapping. By adding this shim header, it allowed routers to handle data more like a high-speed switch while maintaining the flexibility of a global network. To understand how MPLS works, it is helpful to think of it as a postal service for the internet that uses barcode stickers, labels, instead of reading the full address on every envelope at every sorting facility. The process is divided into 3 main stages: label distribution, ingress, entering, and core switching. 1. The setup, label distribution. Before the first packet is ever sent, the routers in the network need to agree on what the labels mean. Routers use protocols like LDP, Label Distribution Protocol, or RSVPTE to talk to each other. They say, if you send me a packet with label 25, I will know it's going to Chicago, and I'll pass it to the next guy. This creates a predetermined path through the network called a label switched path, LSP. 2. Step-by-step packet journey. Stage A, ingress, the label edge router, LER. When a standard IP packet arrives at the edge of the MPLS network, the router performs a one-time, heavy lookup. 1. It looks at the destination IP address. 2. It determines which FEC, forwarding equivalence class, the packet belongs to. 3. It pushes, adds, an MPLS header with a specific label onto the packet. Stage B, the core, the label switching router, LSR, this is where the speed comes in. The core routers do not look at the IP address at all. 1. The router receives a labeled packet, example label 20. 2. It looks at its LFIB, label forwarding information base, a simple table. 3. It performs a label swap, it replaces label 20 with label 35, the value the next router expects, and sends it out the designated interface. Stage C, egress, the exit, when the packet reaches the far edge of the MPLS network. 1. The router pops, removes, the MPLS label. 2. The packet is now a standard IP packet again. 3. The router forwards it to the final destination using traditional routing. 3. Key operations, push, swap, and pop. These three actions define the life cycle of a label in the network. Push, adding a label to a packet, happens at the entry. Swap, replacing an incoming label with an outgoing label, happens in the core. Pop, removing the label, happens at the exit. Note on PHP, penultimate hop popping in many modern networks, the second to last router actually removes the label. This saves the exit router from having to do two tasks, removing a label and looking up an IP address, making the exit process faster. For why this matters, traffic engineering in traditional IP routing, packets always take the shortest path, which can lead to traffic jams on certain links while others are empty. With MPLS, because paths, LSBs, are predefined, an administrator can force certain traffic to take a longer, less congested scenic route. This is called MPLS traffic engineering, MPLS-TE. Summary table, IP routing versus MPLS feature. Traditional IP routing, MPLS switching. Lookup type, longest prefix match, complex, exact label match, simple/fast, decision-based destination IP address, short fixed length label path selection, shortest path only any path. Traffic engineering, hardware mostly software/CPU intensive, hardware based, ASIC. Advantages of MPLS. Multi-protocol label switching, MPLS, is often described as the Swiss Army knife of networking. Its design offers several critical advantages that allowed it to largely replace ATM in the core of telecommunications networks and become the gold standard for enterprise connectivity. 1. Quality of service, QoS, guarantees. One of the most significant advantages of MPLS is its ability to prioritize traffic. Unlike standard IP routing, which is best effort, MPLS uses the traffic class, TC, bits in its header to manage performance. Prioritization, you can assign high priority to latency-sensitive traffic like VoIP, voice, and video conferencing, ensuring they aren't delayed by less critical traffic like email or file downloads. Low jitter, because paths are predefined, LSBs, the variation in packet arrival time is minimized, which is essential for clear real-time communication. 2. Advanced traffic engineering, TE, in traditional IP routing, routers always choose the shortest path based on metrics, like hop count. This often leads to hotspots where one link is congested while a parallel link sits idle. Path steering, MPLS-TE allows network administrators to steer traffic away from congested links and utilize the entire network's capacity. Constraint-based routing, you can set paths based on specific requirements, such as only use links with less than 10 milliseconds latency or avoid certain geographic regions. 3. Efficient Layer 3 VPNs, virtual private networks, MPLS revolutionized how businesses connect multiple office locations. Security and isolation, MPLS uses label stacking to create private tunnels over a shared public backbone. This allows a company to connect offices in different cities as if they were on a single private local network, without the data being visible to other users on the carrier's network. Simplified routing, the customer doesn't need to manage complex encrypted tunnels, like IPsec VPNs, the service provider handles the routing within the MPLS cloud. Faster packet forwarding. While modern high-speed CPUs have made IP lookups much faster, MPLS still holds a fundamental efficiency advantage. Simple lookups, standard IP routing requires a longest prefix match lookup in a large routing table. MPLS uses a simple exact match lookup on a fixed length label. Hardware optimized, this simplicity allows the switching to be handled by ASICs, application-specific integrated circuits, at the hardware level, enabling wire speed performance. Protocol independence, multi-protocol, as the name suggests, MPLS is multi-protocol. The shim layer, because the MPLS header sits between layer 2 and layer 3, it can carry almost any type of payload. Versatility, an MPLS network can transport IPv4, IPv6, Ethernet frames, or even legacy ATM/frame relay traffic using pseudo wires. This allows carriers to migrate to a single modern backbone while still supporting older client technologies. Improved reliability and fast reroute, FRR, network downtime is incredibly expensive. MPLS provides a mechanism called fast reroute, FRR. Local repair, when a link fails, the MPLS router can immediately switch traffic to a pre-computed backup path in under 50 milliseconds. Comparison, this is significantly faster than traditional IP routing protocols, like OSPF or BGP, which can take several seconds to converge and find a new path. Summary table, why MPLS wins. Advantage: benefit to the user, QoS, smooth voice and video, no choppiness. Traffic engineering, better network performance and no congestion. VPN support, secure, easy to manage private office networks. Fast reroute, high availability, internet stays up even if a cable is cut. Multi-protocol, one network.